Welcome back to Applied Mathematics. In this video, I want to talk about properties of equations. There's a lot of vocabulary to go through, so let me get my head out of the way and we'll dive right in. Start off with, what is an equation? An equation is a claim that two expressions have the same value. I want to specifically talk here, what do I mean when I say that this is a claim? A claim can be true or false. When we have an equation which is always true, we call it an identity. When we have an equation which is never true, we call it a contradiction. Identities, I think, are pretty inherently obvious why they are useful. An equation which is always true allows us to convey things very generally. For example, recently we talked about the distributive property that says that A times the quantity B plus C is equal to AB plus AC. This is an identity. It is an identity of algebra that is always true. There's nothing that says that an identity has to be profound, though. It is equally true that 3 times 4 is equal to 10 plus 2. There's no deep meaning as to why 3 times 4 and 10 plus 2 happen to have the same value, but they do both have the same value of 12, so it is an equation. It is an equation which is an identity. It is always true. Contrast that to something like 18 minus 7 equals 21. That is very clearly false. It is not true. Why is it useful to say that? Well, honestly, it's not all that useful to say that 18 minus 7 is 21. It is, on the other hand, useful to have the vocabulary. It's useful to be able to say this equation is never true. There's nothing that makes this equation true. There's nothing good about this equation. We wrap all of that stuff into the vocabulary word of contradiction. A contradiction is an equation that is never true. We now have a label to give an equation that is never true if one comes up. And as we'll see a little bit later, sometimes an identity or a contradiction are sneaky. They don't look like they are always true or never true at first glance, but after doing a little bit of analysis, you find out that that's the case. In this course and in most mathematics courses, we care about a conditional equation. A conditional equation may be either true or false, depending on the values of the variables in the equation. A classic example of a conditional equation is something like 3x plus 7 equals 16. If x is equal to 2, then I get 3 times 2 plus 7 equals 16. 3 times 2 is 6. 6 plus 7 is 13. That's clearly false. If, on the other hand, x is equal to 3, then I will have 3 times 3 plus 7. And that does work out. So For some values of x, the equation is false. For some values of x, the equation is true. This particular equation is a class known as a linear equation. In a linear equation, there is exactly one value of the variable that makes the equation true. There are other types of equations. There are quadratic equations that have exactly two values. There are cubic equations that have exactly three. There are other kinds of equations that have infinitely many. But that phrase of value of the variable that makes the equation true is quite a bit of a mouthful. So a solution to a conditional equation is a specific value or set of values for the variable or variables that make the equation true. Right. We are in this course predominantly going to be looking at equations that have one variable. So when you have one variable, you have one value. If we were looking at an equation that had two variables, that had both x and y in it, then a solution would need to have an x and a y. We'll get to there near the end of this semester. Last bit of vocabulary here is the solution set. A solution set for a conditional equation is a set that contains every solution and no values that are not solutions. That's another one that's not immediately apparent why it's useful in what we're going to be looking at in this course, because we are almost exclusively going to be looking at equations that have exactly one solution. So if we have exactly one solution, we have all of the solutions. There's no ambiguity. But that doesn't have to be the case. There are situations where it's not immediately apparent just looking at the equation how many solutions there are. So by conveying that information in a solution set, we are not only conveying these things are all solutions, but also there's nothing out there that is not a solution. Or there's nothing else out there that's a solution that we missed. So that extra bit of information, that extra bit of confidence can be useful. It's not going to come up in this course. I'm not going to make a big deal about solution sets for equations right now, but it's vocabulary that you might run across, and if you continue onward, it's going to be more important in future courses, so I wanted to include that as well. All right. Onward to a couple of properties. These three properties, reflexive, symmetric, and transitive, tend to come together in the discussions of mathematics. We talk about these three properties as a collective set. The reflexive property is incredibly boring. Anything is equal to itself. So A is equal to A for any value of A. Clearly that's true. And it's incredibly useful in the discussion we had earlier about an identity. If you have something equal to itself, it is true. It is an identity. And so that comes into usefulness in the work that we do. If we end up with an equation that says something like 2x minus 5 is equal to 2x minus 5. It's the exact same thing on the left and on the right. By the reflexive property, this has to be true. 2x minus 5 has to be equal to 2x minus 5, no matter what the value of x is. That is, for a lot of people, so obvious you can't even understand why I'm talking about it, but it is useful, And if you're not accustomed to working with equations, it's not immediately obvious. And I often see students trying to do more work from here. But when you have that, you're done. The symmetric property, again, kind of feels obvious if you've spent any time working with equations, and even knowing the name is something that is more trouble than understanding how it works. But if it's been a while since you've thought about equations, or you're just curious about the vocabulary, the symmetric property tells us that if A is equal to B, then B is equal to A. You can switch around the order of the left and right side of your equation, and there's nothing wrong with that. The reason that this is useful in solving equations is that we are by and large going to be trying to go through several steps of algebra with the goal of ending up with the equation x equals some number. I'll use 7 as a placeholder. Every now and then, when you're working through an equation, you find kind of the opposite happens. Instead of arriving at x equals 7, you arrive at 7 equals x. Well, by the symmetric property, 7 equals x and x equals 7 are the exact same equation. If 7 is equal to x, then x is equal to 7. There's nothing wrong with stopping there. You can take it the one step further if you would like, however makes you comfortable. Finally, the transitive property, which seems a lot more confusing in statement than in fact. If A is equal to B and B is equal to C, then A is equal to C. If you have 3 objects, and the first 2 are the same, and the last 2 are the same, then the first one and the last one have to also be the same. It makes sense. In the work that we're going to be doing in the near term with solving equations, the transitive property is not particularly useful. As we build up, as we start looking at more problem solving, we're going to find more and more places where we end up with, instead of just one equation, we end up with several equations, and combining them together is the tool that the transitive property provides us. So again, things to look forward to in the future. All right. Now, with all of that vocabulary out of the way, we can get to the heart of the matter. How are we going to be using equations? What tools are we going to be using to work with equations? And so, yes, more vocabulary. The addition property, the multiplication property. At least these ones have pretty on-the-nose names that are really easy to remember. And quite frankly, if you don't remember the names of the properties, that's not important. What's important is that you know how to work with them. All right, the addition property tells us that if A is equal to B, then A plus C is equal to B plus C, and A minus C is equal to B minus C. The addition property says that we can add something to both sides of the equation. And since subtraction is really addition in disguise, we can also subtract something from both sides of the equation. As a practical example, the addition property very often shows up when we have something like x minus 9 equals 12. Our goal in solving the equation is to get x by itself. X currently has 9 being subtracted. We can get rid of that subtraction by adding 9. And if we add 9 on the left, The addition property of equality says we also have to add 9 on the right. And on the left-hand side, simplifying this expression, minus 9 plus 9 cancel each other out. We are left with x by itself. On the right-hand side, 12 plus 9 is 21. So that's a very important tool for solving equations. The multiplication property, as multiplication is more complicated than addition, there's a little bit more complication going on here. If A is equal to B and C is not equal to 0, then A times C is equal to B times C, and A over C is equal to B over C. That extra rule of C is not equal to 0, I think that makes sense when you think about the division rule here, right? You can't divide by 0. Dividing by 0 is undefined. So clearly, in that case, C has to not be 0. It's a little bit less clear in this case. But if you think about it for just a second, if you take any equation and you multiply both sides of the equation by 0, you will be left with 0 equals 0, which certainly is true, but is also completely useless to anyone or anything. So we don't want that to happen. We don't want to think about that. We avoid that at all costs. All right, but a quick example here. If I have an equation like 12x equals 72, I want x by itself. X is currently being multiplied by 12. To get rid of multiplying by 12, I can divide by 12. And if I divide by 12 on the left-hand side of the equation, I have to divide by 12 on the right-hand side of the equation as well. 12 divided by 12 is 1. 1 times x is just x. On the right-hand side, 72 divided by 12 is 6. All right. One more example here. Because we can talk about the addition property, we can talk about the multiplication property. Generally speaking, we're going to be dealing with what's known as a linear equation. I'll talk more about linear equations in a future video, but for right now, just a quick example. (7x plus 3 equals 24). This is a linear equation. One of the hallmarks of linear equations is that they involve addition and multiplication and exactly one appearance of a variable. Our goal in solving this equation is to try to isolate x. We want to get x by itself. Currently going on, x is being multiplied by 7 and 3 is being added. If you think about the order of operations, multiplication happens first and then addition. But when you think about solving equations, I want you to think about it as though you are trying to peel an onion. You want to try to get the outer layer removed first and then start working your way in. So in this case, the outer layer, the biggest thing happening is adding 3. So it's the last thing that goes in, it's the first thing that can come out. So 7x plus 3, we want to get rid of plus 3, so we subtract 3. And if we subtract 3 on the left-hand side, we have to subtract 3 on the right-hand side as well. Grouping symbols, plus 3 minus 3 is just 0, and adding 0 doesn't do anything, leaving us with 7x. On the right-hand side, 24 minus 3 is 21. Now we're left with just one operation. There's only multiplication left, so clearly that's the next thing that has to go. We get rid of the multiplication by dividing by 7. 7 divided by 7 is 1. 1 times x is just x. 21 divided by 7 is 3. All right. Hopefully, for most of you, that was a quick refresher. The vocabulary may, again, be something new. I've said it a couple of times during the video, but to rehash, I don't necessarily care that you know the vocabulary in the sense that you can describe. I am going to use the addition property of equality in this step, then I'm going to use the reflexive property. But I do care that if I tell you that we want to use the transitive property, that you have some idea of what I mean when I say that. Moving onward, we're going to be spending a lot more time looking at some equations like this. We're going to look at a couple of ways to make them more complicated. But for now, I think that's far enough. So thank you as always for joining me, and I'll see you next time.